Okay, good morning. We are very pleased to have with us today Professor Yuri Gurevich from Microsoft Research. Yuri was educated at Russia, former Soviet Union, made Aliyah to Israel, taught at Ben Gurion University, right, and then moved to the University of Michigan. After his retirement, he moved to Microsoft Research. Yuri is very active in the field of theoretical computer science and introduced the notion mentioned yesterday of abstract state machines. And he has lots of contributions, both in Volume A and Volume B, something I learned yesterday, theory of algorithms and theory of programs. But Yuri is also distinctive in being very interested in more conceptual and philosophical issues, including the nature of the Church-Turing thesis and the concept of algorithm. So it's, I'm sure we will have fun and also great discussion after lunch. So you are all invited for also to the discussion session after lunch. Please, Yuri.
Thank you. So I'll start with examples. Oops. So this is probably the most classical algorithm, Euclid's greatest common divisor. So you have two natural numbers or two lengths. There are two really different algorithms, but with one program. And suppose there are two natural numbers, A at least as big as B. So if B is 0, then the D is the greatest common divisor, just A. Otherwise, you swap. So it's a well-known algorithm.
This is what Euclid wrote, do in parallel?
They describe in words. Now, if you write it in C, then you should be careful not to do it in parallel.
But he also probably wrote A minus B.
Yes.
Yeah.
So the original algorithm was A minus B instead of mod. So this is a more effective, more efficient version. But I want to emphasize that there are two algorithms there. With natural numbers, it's always false. With lengths, it does not necessarily hold. It holds only the two lengths are commensurate. Here is
Length, you mean real numbers? What is length? Real numbers?
So I specifically say length because that's how Euclid wrote.
No.
Today we would speak
But he exactly
about
wanted real numbers,
real
algebraic numbers at least.
Not,
Right.
not Euclid. I mean, Euclid did not identify lengths with numbers.
yes. Just the notion of real number was not there.
Yeah.
Okay, here is another algorithm, which of the kind that people studied for centuries, also comes from ancient Greece, a ruler and compass algorithm. So you have a red circle C with a center point P. There's another point Q out there, and you want to find a tangent to C through Q. So that's what you want to find. So there is a standard construction. This line, you half it, circle, find this point, and make a tangent. Yet another algorithm, also historical, but much closer. So you have a continuous function f, and you have 2 points A and B, and f of A is negative, f of B is positive, and we want to find the root of the function. So a point here where the value is less than a given epsilon. and you do by halving. Take half distance between A and B, see what happens. In this case, it's still positive. Okay. You half again, check. And by continuity, one can prove that it converges. This is how the sections are called. So wasn't the title problem, what's an algorithm solved by Turing? And consider the examples above. These are 4 classical algorithms. They were called algorithms 200 years ago and 100 years ago. And only one of them can be executed by a Turing machine. The Euclid's algorithm on natural numbers. If you do Euclid algorithms on lengths, you cannot do it on Turing machines. You cannot do those geometrical algorithms on Turing machine, let alone continuous functions. But historically, these are certainly all well accepted as algorithms.
People call the constructions, the Euclidean geometrical construction, algorithms.
Yes, definitely.
Euclid didn't.
So in fact, they have.
Euclid didn't. He just called it a construction or a proposition.
We will call it, at least when I was taught Euclidean geometry, we would call it construction, not an algorithm.
Mm-hmm. Yeah,
But the concept of algorithm, even Euclid didn't use the word
Newton's
algorithm.
iteration was, Newton iteration would certainly be called algorithm.
Yeah. No, I'm asking specifically about the geometric one.
Okay, so I'll tell you a little story. There's a fellow, Wolfgang Reisig. So he told me a story when he took course in algorithm in Humboldt University. Professor started with giving a ruler and compass algorithm as an example of an algorithm. At the end of the course, they finished, and Wolfgang still waited when this algorithm will be addressed. So he asked Professor Shaw, what do we do with this motivating example? Professor got very angry. That's the story. So what does an algorithm compute? So it does not necessarily compute anything. So logicians typically speak about algorithms that compute functions. And then you can speak about input-output relation. But in general, algorithms are much more, do all kind of tasks, and computing function is just one kind of task. For example, an operating system is an algorithm. And what does it compute? By the way, it's interesting kind of algorithm that you don't want it to converge. So computability, in my opinion, is somewhat of red herring. In logic,
Don't say too loud. They're supporting us, assuming that this is not a red herring.
What, the herring company?
It's recorded, Moshe, so we are done for.
It's too late, yeah.
So when we submit the final report for this group, the final report should be one-liner.
Yeah,
Computability is a red herring.
sorry.
okay, it played a central role in logic, but the importance can be disputed. So I think the much more important notion is a complementary notion to uncomputability. So the question somebody, I think Oren asked yesterday, what about the real world? In the real world, what is computable? I think this question doesn't make much sense, because resources are always bounded. It is, you can imagine a little process where you get more and more resources, but also to a point. And then then resources, issues arise with resources, how you measure them and so on. So if anything, it will be closer to complexity rather than to computability. Early on, so when I started, the computability was very, very fashionable. And I I didn't make any social science kind of study, but as far as I remember, there was a kind of naive optimism that if you have an algorithm, you actually can solve the problem. So if you prove certain theory decidable, you can actually decide it. And what is undecidable is sort of too bad. I wrote many years ago a paper against constructivism, traditional constructivism. So sometimes people speak about classical mathematics, constructive mathematics, constructive philosophy, as if these are two equal things. So I think the constructive philosophy was just an error. It is not equal to classical philosophy. And what was the error? They really took this point with computability to the heart. So constructive was recursive. And so they spent enormous amount of time trying to clean analysis to do everything recursively. There was a lot of good things came out of it, much interesting techniques and so on. However, they also missed a lot. They were there 20 years before any complexity theory, and they missed it all. So they were focused or obsessed with this recursivity, whereas in reality, there is all kind of constructions. You can be interested in recursive construction, in polynomial time construction, in much more linear time construction, and even lower or higher arithmetical constructions, and so on. And that's what I should have be doing. So on the other hand, the importance of algorithm is all too obvious. I will not going to make that point. So, ironically, a solvable problem may be infeasible. For example, real arithmetic is decidable by Tarski's theorem, which was much improved, but still it is at least double exponential. And in programming theory, if we had feasible algorithms for at least some interesting cases, it would be huge for programming theory. If you look at specifications, they use so-called additive arithmetic, because it's not just decidable, but decidable well. But real arithmetic, to all practical purposes, is unavailable to us. An unsolvable problem may be quite feasible. I mentioned yesterday this project, Terminator project, which works with C, or maybe C++, I'm not sure now, programs. And they just analyze real-world programs. Typically, people don't nest loops, too many loops, because you write a program, you have to have some understanding of that problem. And they developed techniques which almost always work. So you give them a C program, and they tell you whether it will stop, halt or not. Now, of course, knowing Turing's construction, you can cause them trouble, but not many C programmers bother. Now, computational complexity is also no panacea. Is polynomial time necessarily feasible? Is feasible necessarily polynomial time? So once, many years ago, I had a debate on some conference with Steve Cook. So he was arguing that polynomial time equals feasible. And I was arguing that neither implication holds. So now
The constants, not just the exponent.
he was quite sophisticated. He didn't say that any polynomial time, write something which you can decide it n to the 72, this is feasible. He didn't claim that. What he claimed, that if you take any natural problem, which is solvable in polynomial time, the fact that it's solvable in polynomial time, you have clever algorithm that doesn't just stupidly goes through all possible solutions. And this, historically, what happened, at least at that moment, that every such algorithm, even if initially the polynomial had high degree, the polynomial bounding the computation time. After some work, this degree would go down and relatively feasible algorithms would emerge. So,
Seymour and Robertson proved them wrong.
yes. This
But
is,
there are even simpler things, there are cases, I mean,
wait.
Yeah.
Don't give my lecture. You're right. Right. So, you're right. But this was later.
Yeah.
Then it was not available. So here I wrote, there was a standard algorithm that was working in something like n to the small constant times log n. The power was small constant times log n. But it was natural, it was true algorithm used. And so it is not polynomial, but in order to say for n squared to be as small as that, n should be huge. For this one, I gave him the following example. It was a strange discussion. He gave his talk, then I went, much enthusiasm, and gave this example, which I'll say in a moment. And he said, I need to think about that. That was the end of our public discussion. Okay, but here, the example I gave here was this. So Berkeley stupidly didn't give, this is just a background, tenure to him. So, and he went to Toronto. So I asked him, suppose IRS wants to know whether you paid your taxes the last year you were in the US. Okay. There's a very simple polynomial time algorithm. In fact, linear time algorithm, just to go through all the files. How many files there are? You know, a few tens of billions. But they will not do that. It's completely infeasible. They will never do that. They will find him in log n time using the index. And so here is a simple case which is sort of infeasible. It's feasible in some impractical sense. But, oops, sorry. And this is all about worst case. In addition to worst case, there's average case and quantum computation approximations. The most interesting is this elusive typical case. Because when you say average case, you presume certain probability distribution. And sometimes it is natural, sometimes there is none. So this typical case is very hard. Amazingly, SAT solvers, satisfiability solvers,
yep.
Work. When I saw this effort starting, I didn't believe it would work. I thought that the SAT was just logicians put this particular, happen to have this problem up front. So I thought it's much better to have, say, linear programming for integers, which is also an incomplete problem, but
Integer programming.
Integer program, sorry, to which it's easy to reduce stuff, and amazingly, it just works. So, in my previous group, I recently moved to quantum group, but before a long time it was a group which I actually co-founded, research and software engineering. There are many tools, and some of them do verification or various forms of verification, typically very modest and incremental. And some of them used to use first order provers. Now they all use SAT solvers. Via Z3, we have this very powerful SMT solver for those who know things. But anyway, the grand flaw of all complexity theory is that it is asymptotic. So in all application, typically there is a range of inputs. So for example, IRS, how many files does IRS have? probably more than 10 billion and probably less than 200 billion. So that's the range. So what's the point if you have an algorithm which works when you have trillions of files, which runs quickly?
Actually, the surprising thing is almost that this flawed abstraction gave us was a fantastic guideline most of the time for algorithm development.
Often.
Yeah.
Often not. So if you come to engineering group and improve their speed by 5%, that may be huge.
Yeah.
Whereas complexity-wise, you did nothing.
Right.
And there is also some counter examples where it hurt. I remember talks on Fox, particular talks on Fox, when there was a beautiful algorithm which was n to the inverse function of Ackermann. So something, the function which if you evaluate it on the number of particles in the universe, it's not more than 5. But formally it's not polynomial. And so people worked hard and produced an algorithm which was polynomial with
much worse.
much worse already. Right, so okay. So let me say that this problem of what is an algorithm is very practical. So here is so-called V diagram that you find in some software engineering books. So the point is this: you design some software product. You start with a system design, then you refine, you consider lower level. Again, eventually come to code. There are many intermediate stations here. Then when code is there, you start testing. You test little pieces of code, bigger pieces. At the end, you test the whole system. Now imagine that you made an error here. You will discover it here. After many months were wasted to doing all that and then all that. So what you want when you have your design, to test it right away. You refine it, test it right away, and so on. So that's actually the idea that brought. The idea was a long time ago, but my proposal how to solve it, that's what brought me to Microsoft. So if you consider all these as algorithms, one thing becomes important: the level of the abstraction of the algorithm. So they all speak about the same system, but on different levels of abstraction. We had some small example. I replaced ancient A minus B with A mod B. So it's a higher level abstraction. Now you work faster. Okay. And so if each of these is an algorithm, and somehow in your system you can represent it and maybe test it, then it would be very useful. Oh, I forgot. Okay, is it possible to formalize algorithms? So, not in full generality, because the notion of algorithms keeps expanding. It just didn't mature in its full generality. However, some important species of algorithms, in particular the sequential or classical species, has matured and can be formalized, and some others. So here's an analogy with numbers. So we have integer, rationals, reals, complex, and so on and so on. Do we know what a number is? Can we formalize the notion of a number? And the answer is no, because we didn't finish. there will be more numbers. On the other hand, there are many species of numbers which have been formalized very successfully. So here the situation is very similar. So we have classical algorithms, parallel, actually synchronous parallel, asynchronous parallel, quantum, distributed real-time, more general analog algorithm, hybrid, and so on. And we are not done. There will be more algorithms. For example, I didn't mention learning. But some species, for example, this is the first one, synchronous parallel, interactive, have matured and can be and have been formalized. So why bother? So there are reasons from the point of view of theory. Let me mention this one. Yesterday, David said, take any two programming languages, they all equal. You can program in everything. Everything you can program in everything, in any language. This is not true. It's true in some practical sense. It is just blatantly false. It's true in some theoretical sense. In practical sense, it's blatantly false. For example, take any reasonable algorithm, write it for Turing machine. Yeah. Now, I don't mean Euclid algorithm. Even Euclid algorithm will give you a lot of trouble. By the way, with Euclid algorithm, if you want to, the distinction between two version dimensions will be smashed. Because how will you do A mod B? Most naturally, we are the differences. So one interesting question is, what kind of algorithms can be expressed in language? Call all algorithms be expressed. So I'll return this after the main part of the lecture. In practice, of course, there are many very important practical reasons to bother to formalize algorithms. So this is the body of the lecture will be an axiomatic definition of sequential algorithms.
So one thing that I thought you would say, but you didn't say, is that Turing, and equally all the papers from Church's group, did not define algorithm, they defined computability.
Yes, I'll return. Sorry. So I don't want to not to let you speak, but I'll just return to this question. In fact, I don't mind being interrupted all the time, that I don't lose the time. Somebody counts. Okay. So, foundational analysis of algorithms. That's exactly right here. So, here Turing shines. So, today we'll be in this usual role. For decades, I argued with logicians, because I always speak about Church's thesis. Logicians didn't like Turing machines because they are awkward. You cannot do theory with them. So they always were somewhere there, but it was Church's thesis and the recursive functions, which was the beautiful thing. That's what logicians always investigated. But if you look what this fascinating story, and written many times, how Church had essentially, Church had a lucky guess. Okay. And first time he came to Gödel and asked him that he wanted to publish what became known as his thesis, what he called conjecture. And Gödel said, well, actually I believe you. And then Gödel had visited had a semester in Princeton, where during the semester he came up with this calculus of recursive functions. And Church worked with lambda calculus. So, in fact, he wanted to do using functional alternative to set theory. So he had this calculus and has two great students, Pliny and
Rosa.
Rosa. Thank you. And they were really good students. They had demolished his system. And then he tried to save what is savable, and he worked on this lambda calculus just within for natural numbers, which happened to be a great idea and very useful in programming theory. And then he and Pliny proved equivalence between lambda calculus description of computable functions. As Moshe mentioned, it was all about computable function. What's computable, not about algorithms. At least for Church and Gödel. And then Church was courageous enough and he published his conjecture. There wasn't much by, and he called conjecture sort of cautiously, and there wasn't much convincing power there. And Turing came with a real powerful story, really convincing story that everything computable, computed by Turing machine, under some restrictions. You know, there are different ways to write literature. So some genius like Homer, he lists a lot of names. Everything is voluminous. Now, the author of the J book of the part of the Bible, it's very elliptic. You know? There was day, there was night, word was created. So Turing, somewhat of that kind, he said, everybody is, we compute by writing symbols. Okay? So I have a separate talk and separate paper where I analyze. He gave quite a number of restrictions. So one was the most obvious and blatant from the very beginning. We do symbolic computation, that's it. So out of the 4 examples of mine, only one was symbolic. So it is a restriction. But the convincing power of his was such that it was more than he proved. We saw the method. But what was the standard saying? You my friend, but the truth is more important. So with all my admiration of Turing, my computer in Michigan always was called Turing. Post came with a similar machines. It's not obvious why he didn't publish. In fact, the machines that we know are Post machines. They do work from strings to strings. Turing machines work with infinite inputs. And then there were a lot of people, but there was only one foundational analysis, and that was by Turing. There seemed to be another one in 1953 by Kolmogorov. And so at Kolmogorov, okay, I'll return to Kolmogorov. And that's about it. Because all these models were technical improvements, variations, but not an alternative foundational analysis. So I came to this as follows. In 1980-81, I was in this institute. It was Logic here in Jerusalem. So I was in this institute before any of you. Whole year. It was a beautiful year. And in 1982, I switched abruptly from logic or mathematics to computer science. And Michigan gave me full professorship and tenure, essentially on a promise that I would become computer scientist. This was a very strange time where there was not enough theoretical computer scientists. So I went to chairman and said that I want to teach, give a programming course. And he said, no. I said, why not? He said, we hired you to teach theory. We have enough people to teach programming. I told him, look, I promised you to become a computer scientist. How will I become a computer scientist if I don't deal with programming? So he considered this and said, okay, you will teach it once. So I taught this course once. It was essentially Pascal. Whatever it was called, but it's essentially Pascal. So I taught, happily, was maybe one lecture ahead of my students. And then I discovered something very disturbing. So I had, on Macintosh, a little interpreter, compiled interpreter, Pascal interpreter, and Michigan had a huge mainframe. In fact, Michigan hoped that IBM will adapt that mainframe, that it will become the mainframe for the world. It was competitive, so there were some other universities that used it. And there was a Pascal compiler there, and the two disagreed. So I had examples, concrete examples. My Macintosh interpreter says, no, that's illegal. And compiler on the mainframe had no problem with this, so apparently it was legal. So what is Pascal? So I was quite frightened that students will ask me. So I got from the library all books I could, and they all addressed the questions where the two, my interpreter and compiler agreed. So the subtle issues were not addressed. So that's how I, in a hard way, came to the problem of the semantics of programming languages. So I went and studied denotational semantics and algebraic specification, and I thought they can't be serious. This is good only for the part where my compiler and interpreter agree. For the dirty part, it is impractical. And I tried to argue with these people, but somehow it was, everything should be declarative, and only engineers who don't know any better do things operationally. And so, okay, but I'm running ahead of myself. So another problem, I started to wanted to understand what is computer science about. You know, physics is about elementary particles, or chemistry about molecules. But what is computer science about? And maybe it's not science. No, there is science. For example, when I was a student, we had a course on atheism, which is maybe fine, but also a course on the history of the Communist Party of Soviet Union, which was another sort of pseudoscience. So if something called science, it may be even suspicious whether it's science. Anyway, so I came to the conclusion that it's really all about algorithms. Because, look, programs are algorithms. Programming languages themselves are algorithms. It's kind of universal algorithm. You give it two inputs, a program and an input, and it runs. Compilers, algorithms, operating systems, algorithms, everything is an algorithms. And so the foundational question, which naturally arises, what is an algorithm? And I'm happy to understand, also to learn that it was important for various practical purposes. So what's an algorithm? Kolmogorov in 1953 gave sort of a definition of sequential algorithms. He said algorithms, at the time there were only sequential algorithms. The non-sequential algorithm appeared in the 1960s, at least explicitly. So when in the 1950s, when he said algorithm, it was understood sequential algorithm. So algorithms compute in steps of bounded complexity. Notice that what is bounded is the step. It's a deterministic transition system, and there is a bound independent from the initial state or the for the given program. There is a bound on the amount of work performed at each step. Now, I mentioned that he has possibly he had a different foundational analysis. he didn't write anything about it, but Leonid Levin, his student, I think one of his favorite students, told me that Kolmogorov analyzed computation in physically developing in space-time, and came up with Kolmogorov machine. But in the paper on the Kolmogorov machines, written with his student Uspensky, there is no philosophy, there is no foundations. They just say we wanted to convince ourselves in veracity of Church-Turing thesis and proceed. In fact, they do prove a much more interesting thesis. I'll mention it later. So let me start to formalize sequential algorithms. Let me see. Finish one direction which I probably shouldn't go, but I mentioned. So everybody wanted to work declaratively. Turing machines are not declarative. They are operational. And I came to believe that operational approach is right. And the declarative is actually a misnomer. So people speak about declarative, but really what they want is high level. So declarative programs tend to be high level. Operational approaches tend to be low level with many details. So really what people want is high level, easy to understand program, devoid of dirty details. I think that's what people really worry about. And so the question arises, can you be operational and high level? Certainly Turing machines are not. So can you sort of generalize Turing machines so it works on any level of abstraction? Remember my V diagram. So we need, for every level, we need an algorithm. And so the following story can be thought this way. My first impression was it's too good to be true. But suppose it is true. Let's see how it would look. Suppose we have a generalization of Turing machine which generalizes, which captures algorithms on any abstraction level, and let's see what would it be. So first of all, it's sequential algorithm, therefore it's kind of transition system determined by states and transition function. So if you are a given state, the transition function tells you where will you be, yeah? Or maybe you finished. So two questions remain. What are the states and what are the transitions? As in, I think in 1960s, Knuth said about AI, there are just two problems in AI. What is A and what is I? So something like that here. States. So the notion of states is, as a rule, this is just a joke, don't take it seriously, as a rule defined wrongly in the literature. And I'll tell you why. So typically a state is defined as the values of the variables. So all the variables, you say what values your variables have, and that's the state. Now it seems okay, so why it's wrong? So the programming languages are created very clever. So if suppose you want to learn C. So there are two ways to do it. It's like learn a natural language. One thing you can go sit down with a manual, spend 3 years studying this manual, or some good book, and then hopefully you will speak C. And something else, what everybody does, as children learn languages, you sit down and you start solving simple things. And the design is such that most complexity is hidden from you. You have your variables and you can do, and then you discover, oops, there is also recursion. Now, if there is a recursion, there are more variables. Where are they? They are not visible. So in fact, more generally, so if you speak not C but Java, then there is also what is called where you put your
The call stack.
no, call stack is already in C, where you objects
A heap.
heap. There is also heap, which is a big part. And so essentially, when you stop a program, there's a lot of information there. Most of it is hidden. So state is the whole information which defines, given the program, defines the rest of the computation. So here we speak about deterministic programs, but this definition is more general, even if the rest of the computation will apply even if there are many computations, even if not deterministic.
I mean, even if you just write an assembler and you have to define the state, even then it was clear a long time ago it's more than a variable.
Yes, absolutely. So I don't say that it was so clever that I found something, but the fact is that people give these simplified definitions which are wrong.
Yeah.
So you go to the standard textbook and you see a definition which is wrong. Right, it's not so difficult to see that it's wrong.
Because when you have multitasking, you have to swap the state out, right?
Yes.
And it's much more than just the variable.
And then you know how big it is.
Yeah.
So in fact, a lot of effort is given to reducing the size of state. So for example, in the heap, you keep many objects, and some of them are isomorphic, essentially, in mathematical terms. And people use algorithms for sort of practical solutions for graph isomorphism problem to keep just one copy instead of many copies. So this is a really painful problem, the size of the state. Okay. So now, this was definition was informal, but formally what is a state? And that's, I came to this, it was useful to be a logician. So if you say that logic isn't practical, so this one example which was useful to be a logician, because many years earlier, there was a powerful group of engineers in IBM Vienna lab, and they created Vienna definition language, VDL.
VDM.
No. First it was VDL.
I see.
VDL.
VDM is the methodology.
Right. So VDL, and they said that state is a graph, because they were not logicians. They thought about what can be some kind of general structure, graph. And then they did very sophisticated language, PL1, using this, and it was impossible. So in addition to graph, there was all kind of bells and whistles. Now, Tarski wrote in 1930s a very powerful paper arguing that any static mathematical, okay, he didn't use this word, but essentially any static mathematical reality is a first order structure. By the way, first order is completely not important here, structure. It just, structures happen to be used by first order logic. Second order logic uses same structures, but more restrictive. So these are the structures.
Maybe just to clarify a bit, could you give an example of something that is not a structure? I mean, some abstract object that you will not, that you will not include in this definition.
So it has to be somewhat dynamic. So, for example, if you consider because any static mathematical structure will be any static mathematical reality if you formalize it. So go to Binyan Einstein, catch a mathematician, ask him what you're working on. Whatever he's working on, some kind of structures. Topology.
Which means domain, relations, functions.
Domain, relation, function. Topology, structures. Quantum theorists, they work on Hilbert spaces. Now, if they use also such and such, say, linear operators, put this together, you have a bigger structure. There are Ritz Hilbert spaces and so on. So the example should be something which is dynamic, where something is changing. So this is general. Nothing pretty comes to me immediately to mind. Abstract.
So the more important feature here is the abstraction, really.
Yes.
Okay.
Yes. So structure typically is considered very abstract. The nature of elements is not important.
Okay.
This abstraction is by my daughter.
That's very abstract.
Very abstract. Okay, so I almost immediately came with the first two axioms. First is trivial, and the second by, like, yeah.
Another clarification about the previous one. What's important about states is that they change from one another, right? So I'm missing in this analogy what you mean by structures changing. Is someone looking at the natural numbers and then moving to the real numbers as a transformation of in a meta system?
Oh, no. So consider just integers. You can have a theory of integers. Separate theory, integers. They don't go anywhere, just integers. So similarly here, the role of integers played sequential algorithm. So analogously to study integers, we study sequential algorithms. So integers don't become reals, and sequential algorithms by themselves don't become parallel algorithms or something. So we focused on sequential algorithm. Now, what is sequential algorithm? It starts in a certain state. It comes with a transition function given by a program or recipe. You apply your recipe, you get another state. State number 2. You apply your recipe, you get state number 3, and so it goes. Okay. So this is an algorithm intuitively. Now I want to formalize it to the point that to get a language where.
So a sequential algorithm is dynamic, right?
Yes.
So it's not.
It's
doesn't follow the definition of a structure. You said the structure must be.
So one state is static.
Yeah.
The whole algorithm is dynamic.
Yeah. So an algorithm is I want to ask for an example of a mathematical entity.
Any
which
algorithm.
is not a structure. So that's an example, an algorithm, because it's dynamic.
Yeah. So for example, Euclid's algorithm is not a structure.
Okay. Yeah,
If you
I
think about
understood.
it as an algorithm. Of course, what mathematicians have a trick. Whenever we have something dynamic, they introduce time as an additional dimension
Then you have a structure.
and turn it into a structure.
Right.
Mhm.
So,
Oh, sorry.
We are coming back after lunch, so I mean, if you're not, you have a
Yeah.
little buffer.
Okay. So now the third, I didn't know about Kolmogorov definition, unfortunately. But if I knew, I would be thinking about the problem how to formalize bounded work. So my impression was that it's impossible to do. So I defined this abstract state machine using these ideas, and they work like charm. Everything in the literature was trivially described as an abstract state machine and so on. We were very late. All the people were committed. Some people were doing agentational semantics, some did algebraic specifications, and also I'm not a book writer, so I never wrote a good book. It didn't spread, but there was a big community, still exists. I moved on, but community is there doing this. But practically, we went through programming languages, compilers, everything inside. And everything was trivially formalizable in abstract state machines. After like 15 years, already at Microsoft, suddenly I realized something. So So suppose you have a state. Now think about a state as a big, big thing. Imagine yourself a little ant, and you are on this big state. Now you ant, you're also the control. You want to perform some change. Now you cannot possibly change such a big thing. The work you do within one step is bounded. So all you can do is something around you. You change a little vicinity. The rest remains as is. Okay? The question is, what's vicinity? Because as you do, you move around. And so this intuitive ideas eventually gave rise to this postulate. So there are expressions in the language of algorithm. So for example, in this binary, the bisection algorithm, remember this continuous function, we want to find a root. So this will be the expressions, they call critical expressions. And so what happens if you have two states? Evaluate all these critical expressions, there are only so many of them, and they depend only on the program, on the algorithm. So there's no program, on the algorithm. So if you get the same values, then the change will be the same. So in other words, the ant sees only these expressions. Symbolically, that's all it sees. Now, if you actually execute, you evaluate, and so this is I wrote a little simplified version. So there are these expressions called critical terms that determine the state change. So the delta you need to do. The state change is essentially several assignments. You take, say, because remember what I'm assigning. We have first order structure. It consists of functions. Say function f. Say f of 3 used to be 7. And now we say, okay, from now on f of 3 will be 11. And so this kind of changes. There are finitely many changes and changes. And that's all what is there. So let me quickly finish, and then we will return to discuss it one. And then the definition, sequential algorithm is anything which satisfies the three axioms. And then the question arises, do we have enough axioms? Or, first of all, do we believe all the three axioms? And maybe there are more axioms are needed. And the second question I can answer, more axioms are not needed. Why? Because there is this theorem. So the sequential, this abstract state machines, which I didn't define here, but it is something which is obviously some kind of real thing, which is programmable. If you take any algorithm, it can be state by state simulated by an appropriate abstract state machine. Let's see, I'm about to finish.
No, can you go back there? I don't quite understand. So, one is the definition.
Yes.
And the other one is just to say that a particular formalism
Yes.
is complete for that definition.
Exactly.
Okay.
Complete in a very strong sense, step for step.
Yeah.
Not that it computes the same functions. It is all about algorithms, step for step. And that, if ever we come back to algorithmic complexity, that's about algorithmic complexity. So there is this representation theorem essentially. So I have two slides.
So one of the questions, okay, I'll come back with the question and discussion.
Okay.
Yeah.
So I just want to say that I spoke about sequential algorithms. We pushed it, and with Andreas Blas, we formalized synchronous parallel algorithms. So all models in the literature and we have kind of foundational argument that in any model which ever will be created can be described by this. And there are synchronous parallel abstract state machines which step for step simulate any synchronous parallel algorithm. And then interactive agent algorithms, what I mean, you have an agent which interacts with other. So any such agent, again, formalized completely. But as I mentioned, there are other things which have not been formalized and maybe not formalizable. For example, this one about distributed, I have some ideas of why it's maybe not formalizable. You know, we may have not everything you want to formalize is formalizable. And that's it.
Start the Q&A now, and in a few minutes go down to have lunch, and then continue after lunch.
Yeah. Okay. So let's start now. Questions?
So when you talk to people who do semantics, what they will tell you is that one of the questions that they want to answer is, and this is very much also if you think about, much of the research like in concurrency, they want to capture the notion of equivalence. Okay. For them, it's very important to also know when are two things equivalent. Okay. And so, for example, you could imagine that, and I think you kind of hinted at it, but I don't think you put a formal definition, because imagine we take Euclid's algorithm,
yes.
and I will come up with one structure, and you will come up with a different structure. Yes. We have to decide, is this the same algorithm or not?
Right. So let me, should I repeat the question? So when you go to various semantical system, or to any competitor of ours, they have a notion of equivalence. So for example, in bisimulation, there is a notion of bisimulation which plays an important role as something. If you have two descriptions which are bisimulatable, then you don't distinguish between them. You know, like in mathematics, you have isomorphism and similar things. So here, the most natural notion of equivalence which arises, which we call behavioral equivalence, is that two algorithms have same states, same transition function, and so behaviorally indistinguishable. So the only distinction is syntactical. So one written in C and this written in something else. Now this notion is very, very fine, this behavioral equivalence. And I was explaining zillion of times, and there are people on the other side so clever that, like Gordon Plotkin, got it immediately. But in most cases, they argued with me that this is too rotten notion of equivalence. It's way too fine. And I was explaining the finer the notion of equivalence, the stronger the theorem. Because what we prove, give me any algorithm, and I find an abstract state machine which is behaviorally equivalent. In particular, there's also bisimulate with so on. Now, I should say there is no medicine for all for all diseases. Say the notion of bisimulation, I didn't define it, but something which in process algebras people used. It's a good notion. It's appropriate to certain problems. And we coming with this universal notion of behavioral equivalence do not contribute to this particular thing. So, so having finite state machines does not eliminate the need in process algebra and others, because they address particular problems which require much coarser notion of equivalence, and often for a reason, often not.
No, but now you say the same state, but I mean, we could look at the same algorithm.
I see.
I will use relations, you will use functions. And both are, we could look at it and say, yeah, these are just, people do it all the time. It's a different way to model a state, which, as you know, in reality is some messy object, right?
Yeah.
So we need to a little more than the same states.
Yes. So So same really means isomorphic. Now, we don't have relations, only functions. A relation is a Boolean valued function. So there are trivialities. So I have two values. I call them bool, and I call them true false. you can rename them. So modulo such trivialities, so state should be isomorphic, modulo such trivial renamings. So that's what it is.
What was the point of the talk exactly?
What is the point?
Yeah.
The point is to answer the question. So the big question is, what is an algorithm?
Right.
So I say, this may be an eternal question, like the question, what's number?
No, but your answer. No, your.
Yes. Now I say, but if you consider algorithms like numbers, there are species which matured. So in particular,
Sequential.
sequential algorithm. And what sequential algorithm? We have an answer. We have a definition. There are three axioms. So a sequential algorithm is anything satisfying the three axioms. That's what sequential algorithm is. So that's my answer. And until now,
But can you do anything with that definition? I mean, you call that a sequential algorithm. So what?
yes. So until now, I didn't encounter anybody who gave construct in spite of all my requests. Somebody who said, no, I don't buy this axiom. Or
No, but it's just for the definition you gave it. So there's a definition, but you can't do anything. Can you do anything with the definition other than say
Yes.
a definition?
So I have this definition. I show that you don't need any more axioms. There is a class of machines which go with this definition. And then there was infinitely many studies just for the sake of checking this definition, where we took, I'll give an example. It was an example not from sequential, but from class of distributed algorithm that we did formalize. So there was International Telecommunication Union in UN, and they have their system called SDL. And so after a while they discovered that their system needs to be revamped. They revamped it. Then they discovered again it needs to be revamped but it was so complicated nobody there knew anymore what it was. And so they asked the world, professors, help us. Give us semantics of this damn thing so that we can write a new version. And so bunch of German professors using this competed, and very soon there was nobody else, just them. So there was either them or nothing. And then their system was accepted, and it was a kind of gigantic abstract state machines, in this case not sequential. But for sequential we did many things, just of that sort.
Just defining things. But no, at the end, what do you get? You get a definition of some.
Yes, you get a huge abstract state machine, which gives semantics to the system. You say, what does this mean? The meaning is given by that machine. Now, you say the machine is dirty, meaning should be something mathematical, and I don't buy. I say machine is fine, provided that it is sufficiently abstract. And so they use this machine. So I was, since I invented ASM, I didn't know anything about SDL. So I went to some SDL meeting, gave a keynote, and I started saying that it's surely the first time in this forum somebody speaks who has no idea what SDL is. Just explain what abstract state machines or so on. So this was one example, but there are many examples like that. And unfortunately, I don't know. I thought the world will just take it and run it. So, but it's within. I can tell what happened within Microsoft. So when they came, I tried to hire people from ASM community. So there was a very talented German guy, Wolfgang Schulte, and I was lucky. He just got his habilitation, and I went to Europe, met with him in Vienna, sat in some open cafe, and I tried to convince him to come. And at the end he said, just for 4 years. He is still there, now a big shot at Microsoft. So together we found a very talented group of people, and we created a tool, and the bosses loved it. Bill Gates came in year 2000 to my group, I gave a presentation. He started very skeptical, and then he somehow clicked, and he came with another guy, and the other guy thought it's just all BS, you know, and you know, here's professor speaks as professor, and it's all mathematics, it's all theory, it will never work. And Bill tried to help me to convince him, the guy wouldn't buy anything. And then Bill tried to help us, but it's not a command economy. He can tell people what to do. So often I would get message from some boss that Bill told me that I should look what this group is doing. So the bosses all loved it. People in the trenches, no. Why? Because in order to use this, they had to learn. They had to drop what they were doing, learn this. There is a certain learning curve. In order to sell to people, you need to do something very in small steps. And then European Union helped us. It attacked Microsoft and required from Microsoft. So what happened? Internet Explorer was using deep structure of operating systems. There were special protocols, and it ran fast, and nobody could compete. And the European Union said it's unfair. You write executable specifications. That's how they said. High-level executable specifications, which was music to my ears.
Of the operating system.
No, of those protocols.
Yes.
But there are many of them.
Yeah.
So, and any competitor will create browser using these descriptions. And if something goes wrong, it's your problem. And Microsoft said, we don't have this, we have code. No, we don't want your code, we want high-level executable specification. And overnight, our system, which is called Spec Explorer, became very sexy. So Windows wanted it, and Visual Studio wanted it. And turns out that even though I was told zillion of times, it's impossible to learn, it just will never work. Hundreds of people learn, mostly in China and India, and wrote down all these protocols, often reverse engineering. Let me say one thing, since I don't know, you may be not exposed to software. When you have a declarative semantics, it's a book. So you have a software. There are companies, typically using Z. You ask them, tell me, what is this software about? They write you a book. They write a book several months. Now, engineers cannot read this book, but also software, it's live body. It changes. Whether this book was ever reflecting reality, nobody knows. But it certainly doesn't reflect reality now. And how do you compare? So if you have specification which is executable, you can run it. You can compare, you can test it. And so the reality is such that it has to be executable and high level.
And we
Okay,
pause
maybe,
now.
yeah. So we thank you for this. And we will reconvene